Hello everyone and welcome to lecture 36. We are currently discussing the cost minimization problem of the firm, and in particular in the last lecture we discussed how does a firm decide the optimal input bundle. Well, optimal here denotes the cost minimizing bundle, right? So, what combination of labor and capital will allow the firm to produce a certain quantity of output, but the condition is that it needs to produce that output by incurring the lowest possible cost, right? So, that gave us the cost minimizing input bundle. Now, we want to generalize that idea and derive what is the cost function of the firm. We have seen cost functions earlier in the course, right? So, earlier when we talked about marginal analysis, where we had analyzed the optimal output decisions of a firm which was producing CDs. If you recall, we had a particular cost function, right? That cost function was C as a function of Q equals some expression on the right hand side, right? So, at that time we did not mention, but that cost function was the minimum cost function, right? To produce a certain quantity of output using the inputs, let us say labor and capital, what is the lowest rupee value of cost the firm would incur to produce a certain quantity of output, right? So, we want to generalize that and derive the cost function of the firm, but before that, towards the end of last class, I had left an exercise for you to think about. So, I'll quickly discuss that example and then we will get into the cost function, right. So, the example that I had left you to think about was, so suppose you have a production function Q equals 10 times square root of Lk, right. So, the firm is using labor and capital to produce its output, and the output is related to the inputs given by this production function. Suppose also that the input price of labor is, let us say, rupees 20 per labor hour, right, and the input price of capital is, let us say, rupees 80 per machine, right. So, this is given to us. The question that we are asking is, we want to find the cost minimizing bundle, which is the optimal labor capital combination. I will just put it as L star K star, to produce Q equals 140 units of output, right. So, it is not any arbitrary amount of output that we want the firm to produce. We want the firm to produce exactly 140 units of output, but we would want the firm to produce these units by incurring the lowest possible cost, right. We also want to find what is the rupee value of this lowest cost, right. So, we want to do these two things. So, essentially we first want to identify the cost minimizing bundle L star K star, and then we want to identify what is the lowest rupee value of the cost. Now, if you recall the picture, there are a couple of things that the optimal bundle must satisfy, right. So, if I have labor and let us say I have capital here, and let us say this is my isoquant Q equals 140, this is the output that I want to produce. So, any combination of labor and capital must be points on this isoquant, right. So, the first condition that our optimal bundle should satisfy is the following, right. So, the optimal bundle must satisfies the following two conditions. The first condition is that the optimal bundle, the optimal combination, or rather the optimal input combination of L star and K star must be on the isoquant, right, because otherwise there is no guarantee that the firm will be able to produce 140 units of output. So, here we specifically want the firm to produce 140 units of output. So, I want to choose my labor and capital in a cost minimizing way. So, it better be on that isoquant. Now, the question is, these are various points. So, there is an infinite combination of labor and capital that can be on the isoquant, which will allow me to produce 140 units of output. But all of those bundles are not going to cost the same amount of rupees. We want to pick that bundle which is going to cost the lowest amount of rupees, right. We know from our discussion in the last class that there is also known as a tangency condition. So, notice there are iso-cost lines. Iso-cost lines are going to be lines in the Lk space. So, any iso-cost line is C equals WL plus RK, which means that K equals C by R minus W by R times L, right. So, this is the equation of some isocost line. So, all combinations of labor and capital on that particular line cost the same amount of rupees C, and we are interested in finding out what is that lowest possible C. The key thing also to note here is that every isocost line is going to have a slope which is given by minus W by R units. So, let us think about it. So, minus W by R. So, this is rupees per hour, rupees per unit of capital, rupees per unit of labor divided by rupees per unit of capital. So, units of K upon units of L. So, given that W and R are input prices and the firm is taking these input prices are given. So, unless we are told that W or R changes, the ratio of W by R is going to be the same. So, in this case W is 20 and R is 80 and that continues to be the same. So, there is also what is known as the tangency condition. So, the optimal bundle must also satisfy the tangency condition. Now, recall what is the tangency condition. The tangency condition is one where the isocost line is tangential to the indifference curve, or rather the isoquant rather, I am sorry. So, the isocost line is tangential to the isoquant at some point. So, let me call this point to be point B. So, it is this point B that we are interested in finding. Notice there are many isocost lines in this space. So, this is another isocost line which passes through two potential bundles which also allow me to produce 140 units of output. Here is another isocost line, which is also again passing through two bundles which are allowing me to produce 140 units of output. So, there are possibly an infinite combinations of labor and capital, and through each of those bundles an isocost line is passing. However, they are at different cost levels. Cost is increasing as I move in this direction, notice, and my objective is to minimize cost. So, what I want to do is I want to move in this direction, and the lowest possible isocost level I can go to without violating the output constraint of 140 units is this point B. I would like to be at a lower point here, but notice this does not allow me to produce 140 units of output. Okay. So, with this in mind, let us write down what the tangency condition is. So, the slope of the isocost line, which is minus W by R, must equal the slope of the isoquant, which is the marginal rate of technical substitution. So, if I take the absolute values of the slope of the isoquant and the absolute value of the slope of the isocost line, I am going to get the MPL by MPK must equal W by R, and in this case W by R is 20 divided by 80, which is equal to 1/4, right. So, this condition must be satisfied, which is the tangency condition. Okay. The first point says that the optimal input combination W L star W K star must be on the isoquant. So, mathematically this says that if I choose the L and K, so 10 times square root of LK will be my output, and that should give me 140 units of output. By using the labor capital combination, I should be able to produce 140 units of output. So, if I simplify that, so I can cancel the 10 from both sides, dividing by 10 on both sides, root over LK equals 14. So, let us call this to be equation 1. The second equation is going to come from my tangency condition. So, all I need to compute is the left hand side, which is MPL by MPK. So, let us look at what MPL is. MPL is del Q del L, keeping capital constant. So, that is the derivative of 10 times square root of LK. So, I will take the 10 and the square root of K outside. So, the derivative of root L with respect to L is going to be 1 upon 2 root L. So, this is going to give me 5 times square root of K by square root of L. Similarly, if I have MPK, MPK is going to be the change in output resulting from a unit change in capital, keeping labor constant. So, since my production function is 10 times square root of LK, now I will pull out the L outside. So, I have 10 times root L. The derivative of root K with respect to K is going to be 1 upon 2 root K. So, this is going to give me 5 times square root of L upon square root of K. Okay. So, let us make use of MPL and MPK. So that gives me MPL divided by MPK equals 5 times root K over root L divided by 5 times root L over root K, and I will take the root K up here. So if I simplify this, this turns out to be K upon L, and based on the tangency condition, this K upon L must be equal to 1 upon 4 W upon R, which means that L must be equal to 4K, right. So this is my condition 2. So notice how we are using both these conditions. On one hand, we are saying that the optimal bundle must satisfy the equation of the isoquant, which means I must be able to produce 140 units of output. The second condition that I am imposing is that the tangency condition must be satisfied, which allows me to write that L is equal to 4K. Now notice, if the ratio W by R was had changed, then this right hand side 1 upon 4 will also change. Okay. We will very soon look at a case where what happens with the input price of labor increases. We will handle that separately. Now that I have two equations and I am solving for two unknowns, we can very easily do that. So using 1 and 2, using equations 1 and 2, we can say that square root of LK, so I will replace the L as 4K, so I will have 4K square equals 14, which means 2K star equals 14, which means that the optimal amount of capital that I will use is going to be 7 machines or 7 units. Therefore, since L star is equal to 4K star, the optimal amount of labor is going to be 28 units or 28 labor hours. So my optimal bundle is going to correspond to 28 labor hours and 7 machines, right. So I hope this analysis is making sense, and it is not a difficult example. So we are solving, so keep in mind how many unknowns are you solving for? Labor and capital. If I am solving for two unknowns, I will need two relations. One must come from the isoquant because the optimal bundle lies on the isoquant. The second is my tangency condition, which is to say that the slope of the isoquant and the slope of your isocost line in absolute terms must be identical. Now what is C star? The lowest cost, the rupee value, because notice we also said that we are interested in finding out what is the lowest rupee value of the cost. Well, how do I get that? So since the firm is using 28 labor hours, each unit of labor is going to cost 20 rupees per hour. So 28 units is going to cost 20 times 28 rupees. Then I am using 7 machines, each machine is going to cost 80 rupees. So for 7 machines, this is going to be the cost. So I will have 560 plus 560, which is rupees 1120. So the lowest rupee value of the cost incurred by the firm to produce these 140 units of output is actually 1120, which means that this green line, this isocost line, if you pick any labor capital combination on this isocost line, the cost is going to be 1120 rupees, right. So 560 is going to be the cost of labor, 560 is going to be the cost of capital. So the sum of those two is rupees 1120 is the cost, lowest cost incurred, and that is also the cost of bundle B. So what we have seen now is that 1120 is the lowest cost incurred. So this is an important point, so I want to make a note of this, that the rupees 1120 is the lowest cost incurred by the firm to produce 140 units of output. The other thing that you should qualify the statement is by saying that at the input prices, W equals to rupees 20 per hour and R equals rupees 80 per unit of capital, right. So now you might argue and say that look, even this bundle L comma K, whatever, so this will correspond to some amount of labor and some amount of capital. This is also going to cost the firm 1,120 rupees. Well, that is correct. However, notice this bundle is not on the isoquant. So if the firm were to choose this input combination, it would not be able to produce the 140 units of output. So is the case with another bundle here. So while 1120 is the lowest cost incurred by the firm, at input prices 20, there are many bundles, in fact potentially infinite combination of bundles that the firm could potentially buy using these 1120 rupees. However, exactly one and only one of those bundles, which is 28 amounts of labor and 7 units of machines, will allow the firm to produce 140 units of output, right. So, that is the optimal bundle or the cost minimizing bundle. Now, I mentioned that we had seen the cost function earlier in the course as well, right. If you recall the CD manufacturing firm, this CD manufacturing firm was using some inputs to produce CDs. So, let us say it was using labor and capital, and labor and capital it was buying at some predetermined input prices, right. So, some W and some R. Now, that cost function was 1000 plus Q square by 5000 along those lines. Now, that cost function was also derived using a similar rule, and we are going to now derive the generic cost function. Okay. Now, as an exercise, I will also ask you to think about the following problem. So, let me put this here. Suppose the firm wanted to produce Q bar equals 200 units of output, right. So, right now the firm is producing 140 units of output, but suppose the firm wanted to produce 200 units of output, right. Find the new input combination, input cost minimizing bundle, right. So, you are going to find the new L bar comma K bar, and I am going to keep the input prices the same. W is going to be rupees 20 per hour, R is going to be rupees 80 per machine, right. Now, you will immediately notice from this graph that the level 200 isoquant is going to be somewhere here. So, let us say this is Q bar equals to 200. Now, clearly the point B is not on that level 200 isoquant, right. The point B is here. So, using this 28 units of labor and 7 units of capital, the firm will not be able to produce 200 units of output. Here again I will have to write down the tangency condition. I am going to get a new isocost line which is going to be tangential to the isoquant. So, you are going to get some other line at the input prices which is going to be tangential to this isoquant, and this is going to be some other input bundle, right. So, that input bundle is going to have some amount of labor and some amount of capital. You will again write down the two conditions, that the optimal input bundle is on the level 200 isoquant, and you will also again write down the tangency condition and solve for the new labor and capital combination. So, I urge all of you to try this, it will also give you good amount of practice. And even without doing any algebra, notice that this new bundle, call it as bundle E, right, this new bundle is on an isoquant which must cost more than the bundle B, right. One is pictorially I can see that the blue isocost line which passes through the point E and is tangential to the isoquant at 200 level at the point E is at a higher level than the green isocost line which passes through the point B, right, which tells me that the cost associated with the bundle E is greater than that of bundle B. So, even without doing any math, we can make that claim. Now, what we want to do is, we want to identify the cost function. So, what is the cost function? Which means, instead of saying that what is the lowest cost incurred by the firm to produce 140 units or 200 units or 400 units, what we want to do is, we want to understand what is the rupee value of the cost incurred by the firm to produce any generic Q units of output, right. So, for any Q units, what is the cost? Again, we will make use of the two conditions. One is that the optimal labor capital combination must allow me to produce the Q units of output. So, notice I am going to keep the same output production function Q equals to 10 times square root of Lk. My W and R are also going to be the same, right, I am not going to change that. So, the first condition is going to be that 10 times square root of Lk must be equal to Q, right. Now, instead of Q you can also write it as Q bar, I am just going to write it as Q. So, Q equals 10 times square root of Lk, right. So, that is the first condition. The second condition is going to be the tangency condition, which says that MPL by MPK must be equal to W by R, which in this case is 1/4. Now, notice I have not changed the production function. My production function is still Q equals 10 times square root of Lk. So, the MPL will not change. The MPL is exactly what I identified here. The MPL will be the same. MPK also will be the same. So, the ratio of MPL over MPK must also be the same, right. So, even if I write down the MPL and MPK again, I am going to get the ratio as K by L must be equal to 1/4, which means L will be equal to 4K, right. The only difference then is previously we were using, instead of Q we had 140 units because I wanted to produce 140 units. So, now if I write it in a general form, Q equals 10 times square root of Lk, 10 times square root of Lk. So, now notice what I am going to get. Instead of L I will substitute 4K. So, I am going to get 4K square, which means Q equals 20K, which means K star as a function of Q is going to be Q divided by 20. Now, notice if you had put Q equal to 140, you would have obtained the K star as exactly equal to 7, which is what we found, right. If you go to the previous example, you found the K star as 7. So, for a particular Q equal to 140 units, the optimal K star is equal to 7. So, therefore, my L star as a function of Q is 4 times K star as a function of Q, that is going to be Q divided by 5, right. So, my minimum cost or the cost function C star Q is W times L star as a function of Q plus R times K star as a function of Q, which means my C star is, so W is 20, so 20 times Q upon 5 plus 80 times Q upon 20. This implies that C star of Q is 4Q plus 4Q, which is 8Q. In fact, you can even see that if you plug in Q equal to 140, 8 times 140 is going to give you 1120, which is exactly the rupee value of cost that you got in your previous example. So, if I were to plot this cost function, so cost function is going to be plotted in the output versus rupee space. So, I am going to plot the C star. In general, I am going to get 8Q. So, I am going to get a line like this, right. So, because it passes through the origin, and notice at Q, for Q equals to 140, the cost is going to be 1120. If you want to produce 200 units of output, the cost is going to be higher, cost is also going to be higher, and that value is going to be based on this cost function rupees 1600. So, when you solve this example for 200 units of output, we said you are going to be at a higher ISO cost line. That ISO cost line is going to be associated with rupees 600, right. So, please do the algebra for the example, and you will find that the optimal L and K will be such that your cost is going to be 1600 rupees. Now, why does cost increase as I produce more units of output? Well, to produce more units of output using the given technology, you will need more amount of inputs, you will use more amount of labor, more amount of capital likely, which will therefore mean that your cost also has increased. Okay. So, this is the cost function. Right. Now, this cost function for this example turned out to be linear, right. Now, that has also got to do something with your production function. I will ask you to check that the production function FLK equals 10 times square root of Lk for this example exhibits constant returns to scale, right. So, there is constant returns to scale for this production function, and you can check that if you scale up the labor and capital by a factor lambda, your output is going to increase by exactly the same factor lambda. Okay. Now, so suppose the input price of labor had increased, what would happen? So, let us check that. So, now suppose I want to address the case, what happens when the input price of labor, which is W, increases, right. So, we want to understand this pictorially. Okay. Now, what this means is that previously I had W1 equals 20 and R1 equals rupees 80 per unit. For whatever reason, now the cost of labor has increased from, let us say, 20 to 40 rupees per labor hour, and the cost of capital I am going to still keep it as the same. So, R2 is exactly equal to R1. Now, R2 also could have changed, but it will be easier for us to understand the case where only the cost of labor has changed. Okay. So, the input price of labor has increased, so labor has become more expensive. So, let us see what this means. So, suppose I have the, as before, the isoquant, which is at Q equals to 140. Given these input prices, we had identified that there is an isocost line which is tangential to the isoquant at the point B. We said that this corresponds to 28 units of labor and 7 units of capital. Now that the input price of labor has become 40 rupees per labor hour, the slope, recall any isocost line can be written as K equals C divided by R minus W by R times L. This is the generic isocost line. Now, the W upon R at the new input prices is actually going to be 1/2 in absolute terms. Here it was 1/4. The previous absolute value of slope was the absolute value of 1/4, which is 1/4 units of K by units of L. Now, the absolute value is minus W2 by R2, which is minus 1/2, the absolute value of minus 1/2, which is half units of K upon units of L. Now, that is going to be a line which is going to be steeper. So, let us say that line is going to be here. So, I am going to look at isocost lines which are going to be steeper, have a slope of half, and I also want to produce 140 units of output. So, I am going to get some isocost line which is just going to be tangential to this isoquant, and that point, let us say, is point D. Now, I can repeat this exercise again by solving this cost minimization problem at input prices W2 and 80, W2 and R2, right. But without doing algebra, let us try and understand whether we can write anything meaningful. So, first I want to compare the cost of the input bundle, right. So, I want to write that bundle B, which is this bundle, at input prices W1 R1, which is 20, 80, and I want to compare it with the same input bundle at input prices W2 and R2, which is 40 and 80. So, you are taking the same coordinate, multiplying it with 20, labor coordinate multiplying it with 20, capital coordinate multiplying it with 80, and the same input bundle B. So, labor coordinate multiplied by 40 plus the capital coordinate multiplied by 80. So, clearly the bundle B at W1 R1 must costs less than the bundle B at W2 R2, right. That is not surprising because B is the cost minimizing bundle at input prices W1 R1, right. If you tell me that the input prices are W1 and R1, there is no other cheaper way to produce 140 units of output than using the combination of 28 units of labor and 7 units of capital, right. Rather, let me actually make a correction here. So, I want to compare, make a correction. So, bundle B at W1 R1, I want to compare it with bundle D at W2 R2, right. because B is the cost minimizing bundle at input prices W1 R1, any other bundle at those input prices will allow me to produce 140 units, but at input prices W1 R1 it is going to be costlier than the bundle B. In fact, you can notice that the ISO cost line passing through the bundle D at input prices W1 R1 is going to be at a higher level than the green line, which tells you that this bundle D at W1 R1. Let us make it W1 R1. Yeah. So please make a correction. I hope you are not noting down the incorrect notations. So I wanted to first compare bundle B at W1 R1 with bundle D at W1 R1, right. So I am keeping the input prices the same, and I asked between these two bundles which is the more costlier bundle, right. Now that must be bundle D because the red ISO cost line is parallel to the green ISO cost line. So it must have the same slope as the green ISO cost line, which is minus 1/4, right. So bundle B is the cost minimizing bundle at input prices W1 R1, so it must cost the lowest amount of rupees. Now I want to compare bundle D at W1 R1 with bundle D at W2 R2, which is at 40,80. So now I am looking at the same bundle and looking at at the new input prices, right. So I am looking at the same coordinate of labor and capital. In one case this is 20 times LD plus 80 times KD, in the other it is 40 times LD plus 80 times KD, right. And clearly this remains the same. I am multiplying by 40 here, which is greater than 20. So clearly this bundle D at W2 R2 must be more expensive than D at W1 R1. So what must I write here? So bundle D at W1 R1 costs less than bundle D at W2 R2. So if I combine these two statements and use transitivity, I will notice that bundle B at W1 R1 is going to cost less than bundle D at W2 R2. So what have we shown? We have shown that the cost of bundle B is less than the cost of bundle D, right. So if the input price of labor had increased, I will end up going to a new bundle. In fact, notice I will use lesser amount of labor and I will use more amount of capital, because labor has become more expensive. I am going to substitute labor with capital. I am going to use less labor and I am going to use more amount of capital. Okay. So before I close, one last point. So at these input prices W2 R2, you can solve for, so try to solve for LD and KD, where you are producing 140 units of output at input prices 40 and 80, 40 units of 40 rupees per unit of labor and 80 rupees per machine, right. So please solve this. I will close by simply saying that what we have done is, if I now look at the amount of labor that I am using and the cost of labor, which is rupees per hour, previously the price per unit of labor was 20 rupees per hour, and what did we do? We used 28 units of labor. Then the price of labor increased to W2 equals 40 rupees per labor hour. The amount of labor that I am using, you will notice that is going to be less. So I am going to be using lesser amount of labor. You can also see it from this graph. You will have to solve for what this coordinate is, right. This will be, I tried this, you can check that this is going to be 14 times square root of 2, right. Now similarly, if I take other values of W, I am going to get corresponding values of L, right, optimal. If I were to connect all these points, I am going to get a curve like this. This is the demand for labor, or it is also known as the input demand curve, right. So firm is going to be demanding labor and any demand curve is going to be downward sloping. Higher is the wage, more expensive it is to hire labor, the firm will decrease the quantity demanded of labor. Less expensive is labor, the firm will increase the quantity demanded of labor, right. So, please try this and make sure that the LD is less than 28. What we will do next class is, so today we spent time talking about the long run cost minimization problem. Next class we will talk about the short run cost minimization problem, and we will compare the short run cost with the long run cost. We will do that in our next lecture. Thank you.